All right, now that we've gotten these formulas out of the way and some of the theory behind Laplace transforms out of the way, now we go to the nitty-gritty part where we actually try to solve for differential equations. I don't know how my colors looked like last time, but let's see if I can recreate the sketch here. This is your DE. You're actually your initial value problem, IVP, and you are in the T world when you're working this out. So we have a differential equation here with an initial condition, and then we use techniques like first order linear differential equations or separable differential equations or stuff like that, and then you come to the solution y of t. And then along the way here we use a lot of calculus. So we use some form of integral along the way to solve for that. And the idea is to, instead of use calculus, to go to a different world that we're calling S world, and then solve for something in here using algebra. And what we need to do is we need to somehow make that jump from the T world to the S world using Laplace transforms. So when you do Laplace transforms, you go into the S world, and then you solve using algebra, and then you get the solution. So this has an equation, and then you get the solution. And then in the S world, we tend to capitalize our function names. And then it's called the S world because the independent variable is S. So we exchange our calculus work for algebra work if we're willing to make this transformation to the S world. Now, the tricky part, aside from the transformation to the S world, might be the transformation back, where we take the inverse Laplace transform of our result in the S world so that we can identify our function in T. So this is the basic idea of Laplace transforms. And so let's just try to do a problem that we can do maybe in calculus world, in the T world. All right, let's take a look at our problem. So here's a good problem to start with. Dy dt minus y is equal to 1. Is this separable, or is this first? This is a first order differential equation, so we could probably solve for it using first order differential equation business. But it's also, I think it's separable. Is it separable? I think it's separable, yeah? So my idea is to try to solve for this first using calculus, which is probably going to be pretty easy for us. And then try to look at this from a Laplace transform point of view. All right, so using old techniques, I'll say. And what technique will we use? Let's say it's separable, right? So we could separate it. I think I need to bring the y together into 1, so dy dt is equal to y plus 1, and then I can now separate it. Dy divided by y plus 1 is equal to dt. And then we integrate. Ln of y plus 1 is equal to t plus c. And then we take the exponential. Y plus 1 is equal to e to the t plus c. And then we've seen this before where the e to the c, e to the t can just get combined into a, e to the t. So y is equal to a e to the t minus 1. Now we have an initial condition, so we can plug that in. Y of 0 is a e to the 0 power minus 1 is equal to 0. That's our initial condition here. So I think a is going to equal to what? A is going to equal to 1. So this is a times 1 minus 1. Bring the 1 over to the other side. A is equal to 1. So your final answer is e to the t minus 1. Okay, so, oops, excuse me. So that's using an old technique, and the idea is that if we do this using a different technique, like power series or something, we should get the same answer, I hope. And so let's use Laplace transforms and hope that we get the same answer. All right, so our first task, if you look at our mind map here, we start off with the IVP, and then we take the Laplace, and we get an equation in S, and then we use algebra to solve for S, and then we bring it back to the real world. So this is our path. So let's take our equation, and let's use a different color here. I'll use green. Let's take an equation and take the Laplace transform of this equation. Now, I have dy dt, so that's like y prime. And what I need to do is I need to take a look, and I don't know, maybe hopefully you'll have this memorized by the end of the semester. But you need to be able to do these things quickly. Where if you have a derivative of something, you need n is equal to 1 in that case. You have s times the function that you're looking for minus y of 0. S to the 0 power, because n is equal to 1. S to the 0 power. And so I think we did a couple of these last time. And I don't know how many, what our highest order will be doing, but when n is equal to 2, that's the second derivative. You have s squared times the function that you're looking for minus 1 down from the power. So it'll just be s to the first power times the original function minus minus 1 times the derivative. Okay, so if you have third, fourth, or fifth degree or fifth order differential equations, you'll have 5 derivatives, and then you just follow this pattern when n is equal to whatever the derivative is. So in this case, we just need to worry about this first one in our first problem. All right, so let's go ahead and go back to our problem. The L of that now is going to be s times your unknown function of s. That's what we're going to solve for. Minus y of 0. Little y of 0 is this little y of 0, and that's why these Laplace transforms are solving for initial value problems. You need these initial conditions. Minus y. Now y is just the function unknown to us, and we're transforming that into Laplace world, into the S world. So that's just y of S. And then this is supposed to equal to 1. And let's take 1 through the Laplace transform. A Laplace transform of 1 is 1 over S. Okay, so this is dy dt, this is y, and this is 1. Well, that's what it was back in the t world, and then now we've transformed it into the s world. Now we have this. Y of 0 is equal to 0 according to the initial condition, so this is going to go to 0. And then we're solving for s, or we're solving for capital Y, essentially. So what do we have left? We have s, I want green. We have s, y of s, minus y of s is equal to 1 over s. It looks like we can factor out a y of s here. And then solve for y of s. Okay. So you think, wow, that's cool. Now is the algebra part, right? So we transformed it. Now we're in the S world, and now we have the algebra part. What do we have to do next? What's left is now we found the solution for y of s. Now we just need to take the inverse transform. To take the inverse transform, unfortunately, this is usually the toughest part, we need to take a look at these things as possible candidates of what we have for y is equal to capital Y, and we want to make it look like one of these things, or a few of these things that we're adding and subtracting. The fact that this is linear means if we can have a sum or difference of a bunch of these functions, then we can easily bring that back to the t world, the real world. Now, unfortunately, as I look at this solution that we got, 1 over s parentheses s minus 1, that does not look like any one of these things. But this is still algebra. With some algebra, what we can do is we can maybe separate this. Right? Do you remember doing that sometime in your careers, math careers? So that is partial fractions. We're doing a partial fraction problem. So we need to just be able to separate it, and then something over s minus 1 looks like something over s and something over s minus 1. That's 1 over s minus a here. So if we can successfully get those numbers, then we can use this to inverse transform back to the real world. All right, let's take a look at some techniques for partial fractions. So you got to get good at this partial fraction business. All right, so what we have is 1 over s minus 1 is equal to something over s plus something else over s minus 1. And the fact that s and s minus 1 are linear means the somethings on the numerators are constants. Now, I can multiply by the common denominator, and then that would leave me with this expression, 1 is equal to a times s minus 1 plus b times s. And then what we can do at this point is there's a quick method for doing these things by just covering up one of the values. And what we usually do sometimes is, let's say we let s is equal to 0 and see what happens. What happens when s is equal to 0? B disappears, right? So if s is equal to 0, I have 1 minus a times negative 1. So a is equal to -1. Right? You can do that as long as you don't have any repeated roots in the denominator. Sometimes you have s minus 1 quantity squared, and then so doing that would be a little trickier. So a equals -1. And then now let s equal to the other one that would make the other variable disappear. Let s is equal to 1, and then you get 1 is equal to 0 plus b times s. So b is equal to 1. Kind of wish your Calc 2 teacher taught you that, huh? Because that's what would make one of these variables disappear. So 0 and 1 are our roots. That's a bad part over here. So we don't want to let s equal 0 or 1 from this equation, because then you'll have zeros in the denominators. But once you get rid of that, then you're looking at an expression without any denominators. So it's okay to let s whatever you want. So now your y of s is equal to -1 over s. Let me put it like this. Since we're using what's called linearity, it's like a scalar multiple. That negative sign is actually a -1 scalar multiplied times 1 over s plus 1 over s minus 1. And that's not a big deal, but that's just, I just want to make that absolutely clear. So now, from here, we need to go back to the real world. And that's where we do the inverse Laplace. And instead of doing the formula for the inverse Laplace, let me just take a look at my table of values. I got 1 over s. That goes back to 1. I got 1 over s minus a. A is equal to 1. That goes back to e to the 1t, e to the t. So not a surprise. That's what we got earlier. So your solution is -1 plus e to the t. And that's what we got the first time using calculus. Okay? So, I don't know, the trickiest part would be partial fractions. What's the trickiest part here? Well, think about what you think the trickiest part is. We're doing a Laplace transform. That's our first step. Our next step is to use algebra to solve for this. And then part of translating back, you may need to use, you probably, most likely, or 99% of the time we'll use partial fractions to get this back to the real world. Nick?
I was just going to say, this one was kind of easy to see on the figures.
Is it, yeah. Is it always going to be like that? It could get messy. So if you look at some of the things that we should anticipate, there's going to be 1 over s to some power. That's not a big deal. We have this linear term, but then we also have these quadratic terms with the s squared plus k. So it looks like we're going to be dealing with quadratics where you might have to complete the square. So completing the square is another algebra part of your arsenal that you're going to need to use. And the other part is that we haven't talked about this, but there's, as you complete the square, you might run into an expression that looks like s minus 1 squared plus 25 or something. So that doesn't look like any of these things, but it looks like it's awfully close to this, or if this was a denominator. It looks like it's close to either the sine or the cosine. So there's going to be some rewriting so that you're dealing with shifts like this, some completing the square. So it's all algebra stuff that you might have learned in like Algebra 1 or something, and you think, why would I ever need to learn this kind of business? Whoever needed to complete a square? Well, you know, aside from being able to do that with conic sections, now this is another reason why you need to complete the square. Okay, so little things like that. This is an easy problem to begin with, but we'll take a look at more challenging ones. Okay, so that's a good first problem, and it's a problem that we know the solution to, so that we can easily compare. Let's take a look at another problem, maybe a second order one. Should we get brave already, or the second order is look kind of hard here? All right, 35 or 36? 35, I guess, is a good, just to make sure. Let's do 35. Oh, I didn't set up a problem set from WebAssign. Maybe I should have done that. All right, here's a second order differential equation. So we need the Laplace transform of a second derivative. And you guys have that memorized already? Laplace transform of a second derivative. So let's see. I think it starts off as s squared y of s, and then you start bringing the power down, s to the first power, and then you start your y from the original function, y of 0 minus s to the 0th power, and then y prime. So this is y double prime transformed into the S world. And so these values over here are values that's part of the initial condition, so we can replace those with numbers, and so we don't have any more traces of little y or t's because they all disappear. And then next you have 5. Now, fortunately, this is a constant. Now, if this is not a constant, this whole idea of Laplace will need to go to a different version of Laplace transform where we're multiplying functions. But if it's constants, then because it's linear, we can just take the constants out. And we need to Laplace transform the first derivative. So that's s y of s minus, so s to the first, s to the 0, and then y of 0. And then you have 4 times the y, the original function. Laplace transform the original function is just going to be the big function that you're looking for. And then it's equal to 0. Okay. All right, let's put in some values. We know that the first derivative is equal to 0, so that's gone. The original function at 0 is 1, so we'll change a couple of these values to 1. And now we have just a big algebra problem. S squared, capital Y, minus S times 1, plus 5S. Uh-oh, I have S's and 5's again. You can tell what my 5 looks like, right? Do I have to put a little mark on my S's? 5S, Y. I'm not writing the Y parentheses S. That just means that's just the whole function. So I'm just going to put Y. Minus 1, but that gets multiplied by 5, so let's go ahead and distribute the 5 there just in case we lose it. And then we have a 4, y is equal to 0. All right, I have a couple of terms that don't have an s, or don't have a y, sorry. I'll bring that over to the other side, and then I'll keep the ones with the y's in it on this side, and the same step, I'll factor out a y. So I have an s squared plus 5s plus 4 times y is equal to positive s plus 5. I just changed colors, huh? Let's change that back to green. Okay, so now continuing on here, I get y is equal to s plus 5 divided by s squared plus 5s plus 4. Okay, so this clearly does not look like one of those things. It has a squared in it, but yeah, it doesn't look like one of those two things. So maybe I'll keep it like this and factor the denominator. Can I factor it? Yeah. 4 and 1. So s plus 1, s plus 4. And now I have to break it up. So I'll use, what's that, the partial fractions business to break this up. I have s plus 5 over s plus 1, s plus 4 is equal to a over s plus 1 plus b over s plus 4. And you know the rules for this. I might have to remind you when other weird rules come up, but in this case, you have a quadratic in the denominator, and you have a linear on top, so you can keep it like that, and then you can break it up like this. So if I multiply by the common denominator, I have s plus 5 is equal to a times s plus 4 plus b times s plus 1. And then here's where we do that little trick where we let s equal to, I'm going to make b disappear first. So that would be letting s equal to -1. That would make b disappear. And then a -1 on the left-hand side will give me positive 4 is equal to a times -1 here is positive 3. So a is equal to 4/3. And then s is equal to -4. On the left-hand side, I have -4 plus 5. I think that's 1. And then -4 is going to make a disappear. And I have b times -3. So b is equal to -1/3. So I can rewrite my solution in the S world as a, that's 4/3 divided by s plus 1. So let me write it as 4/3 times 1 over s plus 1 plus or minus 1/3 divided by s plus 4. So that's like a 1/3 on the outside, and then times 1 over s plus 4. So this is ready to go back to the T world. We got it all nice and packaged up. We got 1 over s plus 1. Let's just take a quick peek at what that should be. It looks like it's another exponential going back to the real world, right? except it's plus 1, so make sure you throw a negative in there to make it go back. So back to the real world. We're going to do inverse Laplace now. So we're back to the real world with a little t, or little y, so big Y, is equal to 4/3, a constant, and then you have e to the negative 1 times t minus your constant 1/3, e to the negative 4t. Okay. Any questions? All right. Well, good. This isn't so bad. Nick is still pessimistic there. It's going to get harder. Oh, because of transformation back? E to the AT is equal to 1 over S minus A. So because it's a minus, we have to make sure we look at this as S minus negative 1. And so A is equal to negative 1. And that's the power that comes up. Okay, looking good, looking okay. All right, this is a piece of cake. Let's make it harder now. I mean, let's take a look and dig deeper. Brad? Well, you know, we're coming up with a bunch of different techniques now to solve the same problem. And so in our class, I will tell you which ones to, in the final exam, I'll probably have some first order differential equation where you can solve for it any way you want. And when we get to some second order differential equation, if I want you to solve it a certain way, then I'll ask you to solve it using Laplace transform or series or something. But if I don't ask you, then this is easily done using, we just e to the whatever and then just factor your auxiliary equation. But you in your real life work and when you're doing some physics or engineering stuff and then you come to a differential equation, I think the method of choice is Laplace transforms. And so unless you got a really complicated differential equation where you might need to use series, you'll probably never look at series differential equation again. But Laplace is something that's used a lot in real life. And in fact, they have more shortcuts when you're just finding numeric values in physics and engineering. So, all right, let's dive into more theory here. Oh, I know what. Let's do a problem first and get stuck, and then dive to a theory. Is that better, or do you want to look at the theory first? Let's get stuck. Because, you talk about this translation in the s-axis. Why would you want to translate in the s-axis? It seems kind of silly to do that, but then you really won't know until you're actually doing a problem. So let's do a problem, get stuck, and say, okay, we need some more tools. So I don't know if that's the best way to approach this, but makes it more interesting for me. So this is a problem that you probably could do. It's not separable, but it's a first order linear, so you could probably do the first order linear by finding the integrating factor and stuff like that. So this can be done easily. But let's say we're using Laplace transforms, and that's what we're learning now. So let's see if we can do this using Laplace transforms. All right, let's bring it to the S world, our first step. So the S world, we have a first derivative, so that's the easy, well, I don't know if it's easy, but that's that transformation of S times Y, capital Y, minus Y of 0. Again, there's a little, parentheses, little s here that I'm not writing anymore. You can if you want. And then we have a 4 times y, and y gets transformed into just capital Y because that's an unknown function that we're going to solve for. And then now we have an exponential function on the other side. And so if you remember the exponential function transformation, it's 1 over s minus whatever the coefficient of the power is, negative 4, so it's going to be s plus 4. We have the initial condition of y of 0 is equal to 2, so we can replace that with 2 and then continue on to solve for this. So we have s y minus 2 plus 4 y is equal to 1 over s plus 4. Okay? We want to identify the things that don't have a y in it and look for the things that do have a y in it. Keep it on the left hand. You're solving for y. This is all just linear solving. So I have an s plus 4 associated with a y, and then I'm going to bring the 2 over to the other side, and that's going to require a little bit more work because I'm adding it to a fraction, right? So if I'm adding this to a fraction, I have to find common denominators. Oops, I wanted to do that in a different color. Well, so let's see if we can simplify the top. I have a 2s plus 8 plus 1, so we just call that 2s plus 9 over s plus 4. And then I want to bring this over to the other side, so I'm just going to divide it by s plus 4. So I get this, s plus 4 squared. Okay, now let's see. Some basic ideas behind partial fractions. If you have a repeating linear term like this, you can write it as, I don't know if this will be useful for us, a over s plus 4 plus b over s plus 4 quantities squared. But is that going to be helpful for us? Because remember, we're kind of restricted to a handful of our the table. So let's take a look. We have s plus 4. That looks like it's going to come back as an e exponential, but we don't have an s plus 4 quantity squared, right? We do have s to the n plus 1 power, so we can have s squared. But it's not s plus 4. So here's where we get stuck, and here's where we're going to need a little bit more help and a little bit more theory to continue. We can try to go on and try to break this apart and see what our solutions would be. And this Vanessa, you were asking if that thing always works when you do substitution. Here you have a repeated. It's going to kind of work, and then we'll see how it'll stop working, and we'll have to use a slightly different technique. So let's write this out. I got 2s plus 9 over s plus 4 quantity squared is equal to a over s plus 4 plus b over s plus 4 squared. And then I'll multiply both sides by s plus 4 squared. So I have 2s plus 9 is equal to, I have a and then s plus 4. And then I have b by itself. So I can let s equal to negative 4. And then what do I have left here? Negative 4, negative 8 plus 9 is positive 1 is equal to 0 plus b. So it looks like b is going to equal to 1. But now we don't have a way to find, I don't have any other numbers to substitute to s to find it, right? So how can I find a? Any ideas? Well, this is where we go back to the old way of splitting this up into 2s plus 9 is equal to as plus 4a plus b, and then we match the coefficients. So this first one is, and we know b is equal to 1, by the way, already. So we can take advantage of that. When b is equal to 1, then we're going to get a for this one. But we also know a is equal to 2 from this first one. So I think in either case, we're going to get the same result. So a is equal to 2. And we already know that b is equal to 1, so we don't need to mess with that. All right. This is our little partial fraction on the margin business. Remember when you used to do partial fractions in Calc 2 and you'd spend a whole page doing this? Now it's like a quarter of our page. All right, we are going to rewrite our solution as 2 over s plus 4 plus b over s plus 4 quantity squared. And so we gotta, this is manageable, we know this. This one, we need to figure that out. Okay? So, oh, I put b. b is equal to 1. All right, so here's where we get stuck, and here's where we introduce a theory. It's called the first translation theorem. I don't know. I don't like the word first here. It's really the S translation theorem, because there's going to be another translation theorem which they call the second translation theorem, but that translation is a translation theorem in T. And when I say translate, I mean changing your S into S plus 5 or S plus 4 or S minus 2 or something like that. It's translating in the S axis. So let's call it S translation theorem. And let's look at this. I suppose we could try to prove this using integrals, but I said I was done with integrals today. We did a lot of integrals last time, so I won't prove this, but you can easily prove it using the definition of the transform when you transform. But this says the Laplace transform, if you can identify your solution in the S world, your algebra solution, as something that looks like it's been shifted into S minus A, then you can just multiply your solution that has been transformed by e to the AT. What? Okay, let's write down our answer. Our answer from the previous page was 1 over S, what is it? S plus 4 quantity squared. So what I want to look at is I want to look at this as 1 over S squared, where S changed into S minus negative 4, S minus A. I'm trying to look at this exactly how it's written up here. And I know that the Laplace transform of t is equal to 1 over S squared. Is it? Is it? I should just have a separate sheet for my Laplace transform table. So if n is equal to 1, I have 1 factorial divided by s raised to the 1 plus 1, so that's s squared. That's t to the first power. Okay, so this is a transformation that we're interested in using, along with this shift in the s-axis. So then our solution should be, I'm sorry, I need to put an L inverse sign here. And so to get back to the real world, I'm going to use my shift. I shifted by negative 4, so that's e to the negative 4t times the L inverse of this times t. Okay. Are you guys comfortable in the notation that I'm tossing around here? This is a regular L. This is L inverse. It just means I take the inverse of this, and I get whatever's inside there, the original. So this is the notation that they use in the book, where they do a shift. They're replacing s with s plus 4. And so that allows me to identify what my shift is. My shift is negative 4. So that's going to be the coefficient of the exponential function. Exponential function power. So this should be my result. So now I can go back to this problem, and as we take this back to the real world, we're going to y of t. We have 2 times 1 over s plus 4, 1 over s plus 4, s minus a, right? So that's e to the negative 4t, according to s plus 4, the c, and then no coefficients here, so that's just 1 over, so this is e to the negative 4t times t. And that's your solution. Okay. So with the S translation, we're able to find a solution for, we're able to transform it back to into the T world. Yeah?
Is there any way to check your answer without solving the differential equation?
I don't know. One check that's not going to be enough is to possibly put, just check the initial condition and make sure it works. But that's not enough to actually check if it's correct. So it could coincidentally be correct that way. So the other way to do it is to just solve for this. And we would use, this one's doable. This one's a first order linear differential equation. So find integrating factor on the left-hand side and then work it out, and then we can find a solution for that. But as a quick check, I don't think there is a quick check. No, there is. Well, I suppose you can, take the derivative and put it back to the original function. Yeah, there is a quick check, of course. It's like solving for variables, right? And then put it back into the original equation. So put this back into the original equation. So take the derivative once, take this thing and multiply it by 4, and then it should equal to e to the negative 4t. Yeah, so you can check it. Why did I say you couldn't check it? I don't know. Of course you can check it. Okay. Yeah. Good? So translation. That's the first translation. And then we'll see a translation in the t-axis and see how that'll work out. All right. Let's... is this good? The translation idea good? Should we try to do another one? I can't remember which ones of these problems are the ones where we have to complete a square. Let's see. Can you look at these problems and see if any of them will have a sine or a cosine? 29. All right, let's try to do number 29. We're somehow guaranteed a sine and a cosine in there, right? So let's see if we can tackle that one. Oops. Number 29. Uh-oh. Wait. Do we have a way to transform this? No. Maybe we need another theorem. We're stuck already. Oh, yeah, it's right here. All right, let's see how this is going to work out. Wish us luck. Okay, so I was looking at this and immediately got stuck, and then I thought, whoa, what are we going to do now? Because it looks like our first step is just to transform this, but you know, you can transform things that you're adding and subtracting, but when it comes to multiplying, you can't transform that so easily anymore. Fortunately, that translation theorem that they have, the first translation theorem or the S-axis translation theorem that they have, follows the same pattern where you have e to the x. So let me rewrite the translation theorem that's written here. Let me rewrite it over here. It says the linear transform, or the Laplace transform, of e to the at times f of t is equal to capital F translated by a in the S world. So this is the theorem that's associated with this linear transformation or Laplace transformation. So what we want to do is we want to look at this and say, oh, this e to the t multiplier in the real world becomes a translation in the S world. So we're going to translate by 1 when we get to the S world. And what are we translating? We're translating the cosine. So we need the Laplace transform of the cosine of t. And this is the first time we've worked with this. What is it? It's k s plus the coefficient, which is 1 squared. And on top, I think it's either 1 or s. Which one is it? It's s. So look at if you look at the difference between the sine and the cosine, the sine has a constant up on top, and that constant matches or should match the coefficient of the t, of the angle, whereas the cosine has an s on top. Okay, so this is our cosine function and then our shift. And so given these two pieces of information, the Laplace transform shift, where we have e to the 1 times t times cosine t, says that wherever we see an s in the transform, we're going to replace with s minus 1. So s minus 1 on top, s minus 1, oh, this should be squared, sorry. S minus 1 squared plus 1 in the bottom. Okay? Does that look okay, the shift? All right, so let's take that shift and let's do the linear transformation. So we have a double prime. The good news is that these initial conditions are 0. That will make things a little bit easier for us. We have a double prime, so that's s squared capital Y minus s times y of 0 minus y prime of 0. That's the double prime. The y prime is going to be s times y minus y of 0 equals to what we just found out over here. Our shift is s minus 1 over s minus 1 quantity squared plus 1 squared. Okay? So that's the first step. We transform it. Now we're in the S world. We're just doing algebra after we put in these values, zeros. That's nice. So what do we have left to do in our algebra? We have s squared minus s out of the y's. No other constants to bring over to the other side. And then we have s minus 1 over, I'm really tempted to multiply this out, but if we multiply this out, we might have to complete the square back. We'll just keep it the way it is for now and see if we need to do any more work. So we divide by s minus s squared. So y is equal to s minus 1, s minus 1 squared plus 1 times s. Oh, let's factor this out, because it looks like we might be able to cancel some stuff out. And here we go. Cancel that. So I think we do need to multiply it all out. Should have done that earlier. 1 over s squared minus 2s plus 1 times s. Let's see. 1 over s cubed minus, where am I? Minus 2s squared plus 2s. Can we factor this? Two? No. Did I do the algebra correctly? Well, what's you guys have a quick quadratic formula finder if we factor out an s again? Does this have real roots, or does it have complex roots? Is b squared? It has complex roots? Okay. So if you just, I think we might have to come back here and look at the discriminant. Can I just say d? I can't even read that. I bet you can read any of my notes. Discriminant. So b squared minus 4a is 1, c is 2, and this is going to be a negative 4. The point is that it's less than 0, so we're going to have complex roots. So this over here, s squared minus 2s plus 2, this factor here in parentheses is what we would call is an irreducible quadratic. And the deal with irreducible quadratics is that we can actually take this y is equal to 1 over s squared minus 2s plus 2, and then write it as a over s. And then if you have an irreducible quadratic, and the rules for, this is going back to the rules for partial fractions, you need to have a linear term up on top, bx plus c divided by s squared minus 2s plus 2. So we'll need to solve for this. So this is another case where it that slick little method might not work anymore, and so I'm just going to do Wolframalpha on it. So I want to take apart apartment. So I want to take apart 1 divided by, and make sure I have sufficient parentheses here, s squared minus 2s plus 2. So that looks like the fraction. Is it working, or is it not come up with something? All right, let's just say we did this. And then we got this for the result. So it looks like B is going to be -1, C is going to be 2, and A is going to be 1/2. Should I make that bigger? Oh, wait, sorry. Let's be careful with this. Let me write it like this. This is a 1/2 times 1 over s minus 1/2 s over s squared minus 2s plus 2. You see where I got the 1/2 from? There's actually a 2 kind of hiding over here. Plus 2 over 2, which is 1 over s squared minus 2s plus 2. Okay? Wait, the denominator doesn't look very nice either. Where do we get the denominator from? Do you remember where we got the denominator from? How many people are still with me? We got the denominator from this thing, right? So if we didn't get it from there, or if we forgot, then we would have to look at this and say, ah, man, I have to go complete the square now. So let's complete the square. Oh, there it goes right here. Okay? So let me rewrite it again. 1/2 times 1 over s. We can translate that. Now, I know that's 1, isn't it? Minus 1/2 s over s minus 1 squared plus 1 plus 1 over s minus 1 squared plus 1. Yeah. Yeah? Are we ready to transform it back? No. What's wrong? I can't do it yet. Why can't I transform it back yet? Damn, this thing has too many problems. I can't transform it back yet because there's a shift over here, right? The shifts look like I can just shift it using this transformation back. But I can't do that yet. I can do this, I can transform this, but I can't transform this yet. What's wrong with this? Why can't I transform that yet? No, close. It's an s minus 1 shift, so the top also has to have an s minus 1 shift as well. Can we do something to help this out? What if I put s minus 1 up on top? Can I just do that? I can't just do that, right? What if I put a minus 1 plus 1? Now can I do that? What? This is the same as that. So this is okay. So the reason why I'm able to do that is because I can just split this up now. Into that. All right, so we're running out of time. So maybe I'll just pick up on this because this is looking more challenging than I thought. So what I want to do is I want to go from I just pick it up from here. If you can finish it, go ahead because it should be doable from here. I probably would like to multiply this 1/2 through and then combine this with this other term because these two terms are going to be the same. And so there's a way to combine that. So I'll have, when I go back to the real world, I'll have this one. I'll have this one with an s minus 1. I'll have this one with a constant up on top. Okay? And so I'll have a combination of sine and cosine with a shift, and then this other one that's just hanging out outside. All right, we're 2 minutes past, so I'll stop there, and then we can pick up next time.